Good morning, Michael.
Good morning, Matt. How are you?
Good. I'm looking at this title. What do you mean by points to interval?
Well, we've been talking about functions and approximating them, and we came up with this thing called the Taylor Polynomial. But what's interesting about that is the Taylor Polynomial just looks at one point on the function and says, oh, let me match all the derivatives at that point, and that gives me an approximation to the function nearby.
So what do you mean by nearby? Because that's the key, I think, for pulling this title apart.
Yeah, so the point is when you look at a function, if you look at, so you take some x value, like let's say x equal to 0, you say, can I make a good approximation to the function near 0? What I'd like to do instead is say, how about if we make an approximation on a whole interval? So we'd like to have a good approximation to the function over a whole range of values.
Well, didn't we do that with Taylor by adding higher and higher derivatives, and we could go farther and farther? So why do we have to do this new way?
Well, that's true. You can get a better and better approximation by adding more terms to the Taylor series approximation. That works sometimes. Let's bring up our sine function just to show you what we're talking about here.
Okay, that's a good start.
Okay, so here we go. So here's our sine function. Shoop. Okay, let's look at the interval from 0 to pi. And what you see is we've taken the Taylor polynomial. I've used a cubic just to keep things a little bit simple. So here's our little cubic, x minus 1/6 x cubed. And you see this is the information at the single point 0. We match the slope, and we match the curvature, and we actually match the third derivatives. And we get this nice little curve that follows the sine function pretty well, and then stops. Now, Matt, you're saying, why don't we just add more terms? Well, you could add more terms, but then it's more things to add, and you have more multiplications, like you might have an x to the 17th in there. Do you really want to multiply something out 17 times? I mean, the computer's going to do it, but it's a lot of work.
And you have to divide by n factorial. Like
yeah, so you got to work out the n factorials. If you're doing things like this, maybe you're doing computer graphics, maybe you don't need that much computation. Maybe there's a simpler way. So a simpler way is to say, well, maybe I'll look at this point here, and I'll maybe draw a straight line up to here, and then a straight line down to there. And that gives me a pretty good picture of what's going on. Should I?
Yeah, let's see what happens if you do that.
Okay. So here I mentioned there's 3 points, 0, then halfway through, and then at pi. So I'm going to bump this up to 3 points. Okay, 3 points. And let me show you what the linear approximation looks like. So I've got that line in blue. Now you see it does kind of a lousy job on the initial part of the interval because the Taylor polynomial is doing way better. But then when you get to here, you say, it's actually doing better than the Taylor polynomial because it's following more closely to the sine.
Yeah, because in a sense, you've looked at the interval. You
looked at the interval.
From 0 to the maximum and then back to 0.
And what's interesting is, of course, I can increase n. So here's 4 points, here's 5 points, here's 6 points, and maybe I'll go all the way up to 10 points. And you say, okay, here's 11 points. And you say, wow, that's pretty good. Like you can see it's following the curve very well. And then up here.
Well, it follows very well, but if you look carefully at where the peak is, oops. Right there.
Yeah.
You can see that again there's that cusp
It's a little
at
bit
the
of cusp.
corner. So
one option to do that is you say, well, instead of linear, okay, linear is pretty easy to do, but we saw the cubic with a Taylor polynomial work well. Maybe I can use a cubic like this.
Now, how did you do that?
Now this cubic, it has the interesting thing where it matches the value of the function at 0. It matches the value at the function at pi, but it also matches the slope, okay, which is something the linear function couldn't do. We didn't have enough parameters to adjust that. So here is a cubic, and you can see it gets the nice shape of the sine wave. It's doing better than Taylor's over here. It's doing a little bit worse. Let me add just one more point, and I'll show you what a good job it does.
Oh, it disappeared.
It almost disappeared.
What do you mean it's disappeared?
Can you see it?
Well, not really, because it overlays the sine. Only at the last part near 0 do you see the pink a bit, but it just pretty much overlays and there's no cusp at the top.
So what's interesting is we've got a really close match just using the cubic. We saw that Taylor was a cubic, and it kind of matched okay, except when you got far away from 0. This version matches the sine curve almost exactly. We could do a difference and see how that they are not exactly equal, but you can see a cubic does it really good. So that's the idea of interpolation. Instead of looking at just one point and matching derivatives, we try to match all along an interval by interpolation.
So you're doing this.
Exactly.
And so with the cubic, a cubic is like ax cubed plus bx squared plus cx plus d. So there's 4 unknowns. And with the linear case, there's 2 unknowns, the slope and the intercept, if we look at the usual way we describe it. So thinking about conditions, we have 4 unknowns in the cubic, and we have, when we use a cubic, we use the values and the slopes at the 2 points, like you just did.
Exactly.
And then you put a 3rd point in there, and the slopes and the values match at each endpoint of the interval, which means we have 4 conditions.
Now, let me ask you this, Matt. Do you want to do the cubic example now, or should we do the linear example?
I think we should look at the linear example first.
Okay, so let's put away this graph for now. And let's think about the linear case. And I'm going to make it easy for us because I'm going to say, let's try to find a function and interpolate between x equals 0 and x equal to 1.
That's a great idea.
And so the function is going to have some value here and some value here. This will be f at 0. This will be f at 1. And linear interpolation is a line here.
Okay, so
I'm going to give you this.
Oh, okay.
Can you write down a formula for that little linear line?
I'll just do this first. We'll give axes. And we'll use the expression we've used throughout these videos. So we have y minus y naught equals m into x minus x naught.
Okay.
Now in this case, we'll have x naught will be equal to 0. And we'll call, so this I'll put x naught here, and I'll call this x1. And x1 will be 1, just so we know. And we know that to write everything out, y0 is given is equal to f of 0, and y1 is equal to f at 1. So we have all the parameters we need.
So how is m connected to these things?
Okay, so the next thing to do is to compute m. So m is equal to the rise over the run, so it's f1 minus f0 divided by, in this case, 1 minus 0, because x1 is 1 and x0 is 0, so there's our slope. Fortunately, this makes it really easy.
Very nice.
So that's really nice.
So now you can take all that, you have all the information here, and you can write down this
So
formula.
now we're going to substitute, and for y0, we'll put f at 0. So let's solve for y. Y is equal to y0, which is f0, plus m, which is really nice, is f1 minus f at 1 minus f at 0. There's our m. And then multiplied x minus x naught. So there is at 0, so we just have this. So let's rearrange this a little bit, and we'll see what collect terms in f of 0. So f of 0 is multiplied by 1 minus x plus f of 1 times x.
Great.
Now, the point is, if you look at this, we can actually see we're adding 2 linear functions. And let's see, the conditions, of course, work at x equals 1. This vanishes, and we get f of 1. at x equals 0, this vanishes, we get f of 0. So the conditions are correct. But what we should think of is looking geometrically at what these are. So what does 1 minus x look like, and what does x look like?
Okay, so 1 minus x, it's a line. Starts off at 1, and at x equal 1, you get 1. And this other guy does the exact opposite. Now, what I like about what you've done here, Matt, is we've sort of introduced two special functions. We can call them basis functions. So they're the basis functions for the linear interpolation. B is a nice word for basis function. So B, this is B0 of x. This is B1 of x. And then you can see that the function f, in your nice formula here, you just get f0 times this basis function plus f1 times this basis, oops,
Zero.
0, that's a 1 minus x.
I'll put a 0 there, too.
Yeah, let's put a 0. Plus b1 times x. Now, if you've done some linear algebra, you've seen this before, this idea of you take basis functions and you take linear combinations. That's how we do our linear interpolation. We will take a bunch of basis functions like this. So we start with these basic ones and shift them around to where we need them. And then we multiply them by the value of the function at those points.
At the end point.
At the endpoints.
So now we're really shifting our philosophy to just not just working at endpoints, but values throughout a whole interval. So these basis functions are sitting on the interval 0 to 1.
Mm-hmm.
And so we have two basis functions and two conditions.
Right.
So what's the next step after that?
So the next step, I'm just going to quickly introduce the idea. We want to look at cubics. Okay? So cubics look something like a plus bx plus cx squared plus dx cubed. So there's 4 parameters.
We need 4 conditions.
4 conditions. And the conditions, very quickly, is one of the basis functions. We want to match the function value here, and don't worry anything about there. So, well, maybe I'll say this. We want to match the function values, and we want to match the derivative values.
That gives us 4 conditions.
4 conditions. 4 conditions, 4 unknowns, we can solve it.
So the first basis function is going to look at the value at x equals 0. So it's going to get f of 0 there, but all the derivatives associated with the basis function for this point regarding the values are going to be 0 except for this term here, right? A's got to be equal to 1 because it's going to multiply f at 0.
Right. So Matt, you know what? We're going to end up with a bunch of equations, 4 equations and 4 unknowns. Why don't we do that in the next video?
Sounds great.